Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about photoelectric or quantum pyrometers consist of a crystalline semiconductor material such as indium antimony, silicon, lead sulfide, and cadmium sulfide that respond to photons of radiation from the body they are focused by releasing electrical charges through photoelectricity mechanisms, photoconduction, or photovoltaic. They respond to different parts of the spectrum, so they show great selectivity in the waves in which they operate. And their spectral detectivity is 1 million times higher than thermal detectors. These semiconductors have an excellent signal-to-noise ratio, so that operating in short wavelengths and narrow bands allow precise measurements of low temperatures. The output signal depends on the instantaneous temperature of the detector volume, thus avoiding the delays due to the increase in the temperature of the detector mass that exists on other models of thermal pyrometers. The electrical voltage generated by the detector is calculated with the formula displayed on the screen. An insufficiently approximate estimate of body emissivity can lead to errors that can be minimized if a short wavelength, a small bandwidth instrument is selected. For example, a 10% error in emissivity represents an error in the instrument indication of plus minus 25% at 1750 Celsius and plus minus 75% at 3000 Celsius, while a 25% error in emissivity leads to an error of plus minus 75 Celsius at 1700 Celsius and plus minus 190 Celsius at 3000 Celsius. One of the methods to amplify the signal is to interrupt it by means of a loaded disc at several hundred Hz, thus obtaining an alternating current signal that can be amplified. In applications in the glass industry, such as measuring the temperature of falling glass drops, the instrument works with wavelengths of 4.8 to 5.6 microns that give minimal interference with water vapor, carbon dioxide, and sunlight in the range of 35 Celsius to 540 degrees with a time constant of 0.2 to 0.5 seconds. The instrument with a photoelectric detector for general use has a working field of 15 to 3000 Celsius, can focus from 1 meter to infinity, has a time constant of 2.20 to 200 milliseconds, and can reach response time of nanoseconds, which is perfect for temperature changes or rapid movements of the process when the electrical noise that accompanies the measurement is within acceptable limits. Ttwo-color pyrometer is based on the fact that the relation between the radiations emitted in two narrow bands of the spectrum is a function of the temperature and the relation between emissivities of the body corresponding to the two bands. The instrument has an emissivity radio selector. If the selected radio is correct, the device can indicate the actual temperature of the object with a great accuracy. Its use is excellent in gray bodies that have a constant emissivity for all wavelengths. On the other hand, the pyrometer allows measurement to the atmosphere of smoke, steam, and dust, since due to its operating principle, the reading is theoretically independent of the absorption of the intermediate atmosphere. Here, we can see a graph of the emissivity of a tungsten filament from a halogen projection lamp operating at 60% current intensity, compared to monitoring the emissivity curve by a two-color pyrometer. This pyrometer divides the radiation of the object in two beams, measured by two similar silicon photoelectric cells. One of them has a filter that only lets through the radiation of the shorter wavelength, that is 0.5 microns, and the other in the 0.9 microns area. The relation between the two outflow currents of the cell is a measure of the temperature of the object. The pyrometer is susceptible to electrical noise, since the differences in intensity in the two bands are relatively small, and also as the relative emissivities are less known than the absolute value of emissivity. The errors can be very large if a color is more affected than the other because of the environment or changes in the material. The laser technique applied in pyrometer solves these problems, so that on a surface with an unknown emissivity, A laser beam that is reflected from the surface provides an emissivity value close to the unity. And well, this will be all for today's video. Don't forget to give me a like, subscribe, and share. I upload videos every Wednesday in Spanish and every Friday in English. Adios! The instrument. Adios.